volume, much cheaper, right? Well, it doesn't work out very well, as you see in the movie. So Wired sent me out to Stanford and MIT to write about a new technology called optogenetics. Now, it doesn't sound like a very sexy word, optogenetics, it sounds like use the glasses, look at genes, what is optogenetics? But I realized that it is one of the most profound new technologies for examining neural activity. What you do, in a nutshell, is you genetically modify neurons by giving them genes that come from plants. And you give them the genes that make plants respond to light. When you do that, the neurons then respond to light as if they were plants. It's really mind-blowing stuff. So let me walk you through some basic optogenetics. So first of all, let me just talk about the limitations of current technologies. We know that you can stick an electrode in a brain and use that to fire neurons inside the brain. That's done in my cochlear implant. It's done for people who have Parkinson's disease. You put electrodes in the brain to fire certain areas of the brain to make neurons do stuff. And it does work. But there's a big limitation. The limitation is it's very imprecise. In the brain, there are actually thousands of different kinds of neurons. It's not just an undifferentiated soup of all the same neurons. And we cannot, with electricity, fire only one kind of neuron, leaving the rest unaffected. That's important. If, for example, to help Parkinson's, you want to fire the motor neurons, and you want to ignore everything else. But we can't do that. When you fire the motor neurons, you also fire all the other neurons, and you get all sorts of side effects. So here's what optogenetics does to fire only one type of neuron. What you do is you take genes out of plants, channelrhodopsin and halorhodopsin. And channelrhodopsin is basically a gene that will make a plant cell react to light. Halorhodopsin inhibits its reaction to light. You take these genes, put them inside a virus, inject the virus-bearing fluid into the brain tissue, where the virus infects all of the neurons. In other words, it transports the channelrhodopsin gene and the halorhodopsin gene into all of the neurons in that small area of the brain. So far it seems like we haven't gained anything, right? We put these genes in all the neurons. So what? Here's the so what. The so what is that you can add promoters that will only allow one kind of cell to use the new gene. So we all know that in DNA, different cells will use different pieces of DNA. That's what makes a neuron different from a cell in the stomach, and different from a cell in the muscle. They're all reading different parts of that DNA. And they do it by using promoters. So you can attach promoters to these genes so that only cells of type B will actually use the gene that you put them in. That's the beauty of the scheme. So in other words, to illustrate, let's say I want to fire a neuron of type B. I shine blue light at it, and that makes only that neuron fire. Because it and only it recognizes the promoter in the new gene that we put into it. The other cells have the gene, but they don't use it, they don't recognize it, so they don't fire. So optogenetics gives you very precise control over just specific kinds of neurons. It also goes the other way around. So let's say a neuron of type B is firing, and you want to stop it from firing, which is just as important as making the cell fire. In computers, 0 is as important as 1. The absence of the signal is as important as the presence of the signal. So you shine yellow light on it, and that inhibits the neuron from firing. Why blue, why yellow? Well, the fact is that these genes are sensitive to light of specific wavelengths. So blue is 470 nanometers. Yellow is some other frequency spectrum. I forget what it is. Basically, the cells are sensitive. The genes are sensitive to specific wavelengths of light. So you can imagine a system where you genetically modify the neurons in parts of the brain, insert LEDs that shine lights at them, and use that to turn on and off specific types of neurons at specific times. So that's optogenetics 101. Any questions at this stage? Yes?
How deep in the brain can this work?
Okay, great question. How deep in the brain does this work? Well, it works only as far as light will penetrate. So if you put an optogenetic array in the surface of the brain, at the cortex, it will penetrate maybe a millimeter or two, which is still reaching millions of neurons. Now, most of the activity that we call cognitive happens at the surface of the brain. Most of what we think of as dreams, memories, language, happen at the very surface of the brain, which is very easy to reach. You could just put an LED array on top of the brain, in between the skull and the cortex, and use that to shine light into the tissue. So to do the kind of things I'm talking about, you actually don't need to go that deep into the brain. Okay, so to wrap up my discussion of optogenetics, it enables this precise control of neurons. Now, in the book, World Wide Mind, I go into detail behind the use of technology to alter functional groups of neurons, just the neurons that I recognize an apple, or recognize a name, or recognize a face. There are these really exotic technologies you can use to recognize neurons that have just fired, index them, and then make only those neurons fire again, making it theoretically possible to force a brain to imagine an apple, to force a brain to imagine having heard a name in theory. So this is a theory that I build on in the book. Let me show you in action now. So I'm going to show you a video, which doesn't look all that spectacular, but it really is. So I'm going to let you watch it twice. So the first time I'll just let you take it in, then I'll explain what's happening, then I'll let you watch it again. Here we go. So basically, you can see a mouse running in a counterclockwise circle. Okay. Okay, wow, exciting, right? You all are straining your thrill of this. Now, let me tell you what's going on here. There is a fiber optic cable that is extending down into a plug that is screwed into the mouse's brain, so that researchers can shine a blue light down the fiber optic cable so that it will illuminate the brains in the mouse's brain. Now that mouse has had part of its brain genetically modified so that the neurons in its motor cortex will fire when they see a blue light. So they put the virus-bearing fluid into the motor cortex, and they did it in the motor cortex in only 1/2 of the mouse's brain. Every brain has 2 hemispheres. This hemisphere controls this side of the body, this hemisphere controls that side of the body. So think about it for a minute. If I was a mouse, and you wanted to make me run in a circle, okay, the circle going this way, you would shine light into genetically modified neurons on this side of my brain, making these 2 limbs run forward. And then my other 2 legs would just go to keep up, and I'd end up running in a circle. Okay, do you see that? Basically, if you tied down this leg, only that leg could go, I would end up running around in a circle like that. So this is what's happened. So the mouses have 1/2 of his brain genetically modified, and just the motor neurons in that half of the brain. So when the blue light shines, half of the mouse's limbs start running, forcing it to run around in a circle, and specifically a counterclockwise circle. So now I'll run it again. So right now the light's not on. In a moment you'll see it turn on. So there you go, the blue light just went on. It's now illuminating the mouse's motor cortex, forcing the motor neurons of half the brain to fire, making it run around in a circle. Then the light turns off. The mouse just goes back to what it's doing. It looks up, what the heck just happened? So this is demonstrating the ability to precisely control one particular kind of neuron